everybody. Today I'd like to talk to you about some of the guidelines, tips, and hints that we'd like you to follow for the graphs that you create for Physics 2210 and 4210. So first let's go ahead and define what we're talking about. When I speak of a graph or a plot, graphs are means of summarizing the large amounts of data so that the results can be easily understood. And then sometimes from that graph you can get new data or new ideas that you can extract from the graph that would be hard to get otherwise. For example, if you need the slope of a graph, then you can do the analysis on that. From the data then you can extract the slope, and that might give you some new information. Now in this lecture we're going to summarize good graphing practices, and we're going to cover linear, semi-log, and then log-log graphs. So first, let's talk about some basic components of a graph. Now on these next two slides, these components of a graph that I'm going to talk about are summarizing the different components of the graph that should appear in the graphs that you create for the talks that you give later on in Physics 4210 and for the graphs that appear in your lab reports in Physics 2210 and in 4210. Okay? So, first of all, looking at this graph, the horizontal axis is called the abscissa. The vertical axis is called the ordinate. But to be honest with you, very rarely can I recall those words. I end up just calling them horizontal and vertical axes. So there you go. Now, every graph that you produce that you present in a talk or on a poster, for example, those should have titles. Now, if you're putting a graph inside of a paper, instead of a title, you'll have a figure caption, which will usually appear below the figure. So you'll call it figure number 6, and then you'll say what the figure is in the caption. So if it's a talk, you have a title. If it's in a paper, you have a caption. This is a talk, so here we have a title. Average flux rate versus position for the 225 degrees Celsius crucible. There you go, that's the title. Now, the titles have to be clear, and they have to uniquely identify the graph. You also don't necessarily want them to be too wordy or too long, but it has to be specific enough so that people know what you're talking about. In other words, a title shouldn't be graph 1 for a talk. That's not okay. The independent variable you're going to put on the horizontal axis, the abscissa, and the dependent variable you're going to put on the vertical axis, your ordinate. And the scale should be easy to read. So the tick marks that are displayed on the graph should be large enough so that if you can see it, you can read what the numbers are. And they should be spaced far enough apart so that when you plot your graph out, that the numbers don't overlap with one another, that they're easy to read. So you can see here I've got a lot of space between the numbers on these tick marks. Okay? Continuing on, you want the data to fill the space well. In other words, it shouldn't be that all of your data is up in the top or up in the left of the graph and then you got a lot of white space. You don't want that. Now sometimes that means that you're not going to be able to include the 0, 0 component on your graph. Okay, you're not going to be able to include that. All right. So, for example, in this data here, in order to get the data to fill the graph, I just ran the vertical axis from 0.04 to 0.1, and then the horizontal axis from 160 to 240. See, the 0, 0 point's not there, and that's okay because it allows the data to fill the screen. Okay. Now, the axis labels need to have words with units if it's not a dimensionless number. Okay, so here we have distance from the crucible, and then in parentheses nm for nanometers. So you've got what it is, and then you have the units. It's very important that you have units pretty much everywhere. Okay, you're going to want to, for your data points, to have them be pretty small symbols. You don't want huge symbols, but you also want to be able to see the symbol. Okay, so a decent sized symbol but not too big. And if you've got multiple sets of data plotted on one plot, then you'll need to have each one of those symbols have a unique shape. Okay? Here we've just got one data set, so they're all squares. Now you should also see here I've got a red line, and that's a linear fit to my data. So if you're doing that, if you're doing a fit to your data in some form, then for 2210 and 4210, we want you to also put the equation for the fit on the graph as displayed. Okay, now one thing about this fit equation, you can see there's numbers there, but then there's also units. So anytime you have a number, you should have a unit. Also, if it's one number that you're showing, anytime you have a number, you should have an uncertainty associated with that. And so here, for example, it's 6 plus or minus 0.3. Okay, so there we're showing the uncertainty that we extracted from that fit. Okay, so proper units, proper symbols, uncertainties everywhere. We want you to dot all your I's and cross all your T's. All right? So those are some of the components that we want to see in your 2210 and 4210 papers. Now, error bars aren't always drawn on graphs, but really they kind of should be if you've taken the data experimentally. If the uncertainty on each data point is so small that you can't see it on the graph, then for example in the figure caption or below the figure somewhere, you need to say that that's true. Say the error bars are as large as the data point or something like that in the caption so that people understand that. Okay? Now I've got some examples of error bars here. A is kind of the general case, and you can see that there's vertical and horizontal error bars there. Okay? So you've got your data point, your symbol there, that circle, and then the bars with the line on it indicating where the error bar falls. Okay? Now sometimes if your uncertainty in the x direction is really small, and the horizontal direction is small, you're going to only show the vertical error bars. That's what it's going to be like for your first assignment using the origin. Now, the real truth of error bars are, though, that they don't fully describe where the data point might lie, and also it's not like it's a rectangle, okay? So if you're looking at a data point, you should draw yourself a little oval or circle around that data point and mentally draw that and understand that the true value could lie anywhere in that circle. We're going to talk more about confidence limits later on as we go in the course, but basically the oval shows the uncertainty region where you're 95% confident that the true point lies within that bound. Okay? So that's what we've got there. Now most of the time in 2210 and 4210, you're going to be generating plots from a tool like Origin or Excel or some other data analysis program. However, sometimes you might be asked to do a graph inside your notebook or something where you're drawing it out. Okay, so if that's the case, then you should still follow a lot of the same rules that you follow for the computer-generated graphs when you draw it out. You should still have a title, you should still have error bars, you should still have reasonable units that are displayed, all that kind of stuff still holds. Okay, so you can see on this graph we've got clearly labeled title there, we've got axes labels that show the units, we've got tick marks that are spaced far enough apart, we've got large labels for our numbers on those tick marks so you know where you're at, the graph fills the available space, all those things are still holding for this hand-drawn graph, so that's nice. So this is a good example of a linear handmade plot. Okay? Now, of course, the generic equation that you learn in algebra or whatever for a linear plot is y is equal to mx plus b, right? Everybody's learned that. So here y is your dependent variable, x is your independent variable, m is the slope of that line for a linear fit, and b is the intercept for that linear fit, okay? So that's all there. Now, you don't have to, this is important, when you're putting your equation on the graph, you don't have to put it in y equals mx plus b form. So for example, this is an example from introductory physics. If the final velocity equals to the initial velocity plus the acceleration times the time, then instead of y is equal to mx plus b, for heaven's sake, right, vf is equal to vi plus at, right? That's what you want to write. You don't want to write y is equal to mx plus b for everything. Okay, so use whatever equation you're actually trying to fit when you display your equation on that plot. Okay? Slopes have units. Okay, so be sure to include any units in your equation. Make sure that those units are there. Now, let's talk about linear graphs versus semi-log graphs versus log-log graphs. This is a linear graph. One of the reasons that I'm showing you these hand-drawn graphs is because I think it helps to think about linear graph paper versus semi-log graph paper versus log-log graph paper. Okay, so this is regular old graph paper, and you can see that there's lines drawn on the graph paper, and the lines form little squares. Okay, so on linear graph paper, you count over 1, you count up 1, and it's the same distance when you count over 1 and up 1. Okay, so on linear graph paper, a straight line will have the form y is equal to mx plus b. Okay? But sometimes you might have functions that you want to plot out, draw by hand, or even, plot on a regular graph, where you've got something dependent upon a power of some kind. And in that case, it might be easier to look at a log-log plot or something like that. So let's review a little bit about logarithms to remember what's going on here. Okay, so let's talk about base 10 logarithms. The base 10 logarithm function gives you the power of 10 of that number. Okay, so the log of 10 to the x would just be x, because you're extracting the power that you're raising 10 to from when you take that logarithm. So what that means is the log of 0.1 is the log of 10 to the minus 1. That's what 0.1 is, it's 10 to the minus 1. And so the log of 0.1 is minus 1. The log of 0.2, that's the power 10 to the power of negative 0.7, and so you're extracting negative 0.7 when you take that log of 0.2. Okay, so what logarithms do is they take very large or very small numbers and make it more manageable, and that can be useful if you have data that span many orders of magnitude, because it puts the data points on the plots that you generate closer together on the plot. It kind of squashes it in and enables you to look at it in a more compact way. Okay? Now there's some rules for powers. For example, if you're multiplying 10 to the x times 10 to the y, then that's 10 to the x plus y. So for example, 10 squared times 10 cubed is 10 to the fifth. So if you take the log of two multiplied values, then it becomes a sum. So the log of AB is equal to the log of A plus the log of B. Okay? And then the log of 10 to the x times 10 to the y is log of 10 to the x plus y, which is equal to x plus y. All right, so all that in review, I hope. If not, there's some good resources on the web that you can look up, or I'll link to, and you can review those rules. Okay, so remember also that log of 10 to the x to the power of y, you multiply that power then, so you get 10xy. So for example, 0.1 squared is 10 to the minus 1 squared, which is 10 to the minus 2, which is 0.01. So that means that if you take the log of something raised to a power, then the power multiplies that logarithm. So here you have log of a to the b power, and then that's equal to b times log of the a, right? So these are all some rules. So make sure to look back over those to make sure that you understand it. Okay, given all that background information on logarithms, let's now examine log-log graphs. So this is a good example of a log-log handmade plot of the period of a pendulum. So let's remember the period of a pendulum, the equation for that, the period t is equal to 2 pi times the square root of L over g, where L is the length of the pendulum and g is 9.8 meters per second squared. Okay? So let's think about this. What this basically is, if you plot the pendulum length on the horizontal and the period on the vertical axis, then what you're doing is you're taking the pendulum length and you're raising it to the power of 1/2. When you take the square root, you're raising something to the power of 1/2. So let's discuss what happens when you take a variable and raise it to a power, and then plot that on log-log paper. So let's generalize this function a little bit, instead of just considering periods of pendula. So let's do y is equal to a times x to the n. Okay? So if you were to do that on log-log graph paper, you're going to get a straight line. And that's because you're taking the logarithm of both sides of that equation. So here, the log of y would be equal to the log of a x to the n. Breaking that out, you've got a times x to the m, so you've got log of a plus m times log of x. Okay, so that's how that would break out. Now, if you're plotting it on log-log paper, then this is a linear equation that has a slope of m. Okay, so on this hand-drawn log-log plot, where you have this graph paper that's a logarithmic log-log graph paper, the boxes on the graph paper aren't all the same size. They're not evenly spaced. So you can see that they start off, the boxes are spaced further apart, and then they get squished together until it goes up to the next power of 10. So that's what log-log paper does for you. I have some posted on our course website, and of course these slides are made available on our course website for you to examine. So what the paper does for you is it kind of just already takes the logarithm for you. It already takes that logarithm, and then you just count over boxes, and it does it for you. You just plot your data points, and it's already, if you follow those rules, a straight line. That's why log paper is done, okay? So you just count and plot the points. Sometimes it's helpful to go ahead and relabel those numbers on the axes that are automatically generated for you on the log paper, rather than just leaving it as 1, 2, 3, or whatever, okay? So going back to our equation and thinking about our pendulum now, instead of y is equal to ax to the m, let's think about what this really is. Now here, you've got your vertical axis. Our variable is going to be the period t. So instead of y, we're going to say log of t. Now, the constant a would be anything that's multiplying our variable L for length of the pendulum. So that 2 pi square root of 1 over g, that's all constants that get sucked into that a. So this becomes log of a becomes log of 2 pi times the square root of 1 over g, and that's just a constant. So this now becomes our intercept in our linear equation. This log 2 pi square root of 1 over g is our intercept. Now, the rest of it is 1/2 times the log of L. Remember, L here, you're taking the square root, so you're raising it to the power of 1/2. So that's where the 1/2 comes from, and then the log of L is there, okay? Now, the graph paper goes ahead and fixes the logarithm for you, and so the slope of this line is going to be 1/2, okay? So this log paper takes a function that is not linear and linearizes it for you. All right, so that's what's happening there. Okay? Okay, let's talk about natural logs really quickly. So natural logs follow the same rules, but they're, instead of based on the power of 10, based on 2.781828, which is e, okay, as a base instead of 10. This is a special number because it's the only function that you can take the derivative of, and it's the same. The same. So if you take the derivative of e to the x, you get e to the x back. So it gets used a lot in physics because it's special in that way. Now if you take the natural log of e to the x, you just get x, okay? So the natural log of 1 divided by 2.781828 is the natural log of e to the minus 1, and so you get minus 1, okay? Now of course you can switch your base. 10 and e are special, but you could really use any number to raise things to the power of. There's the rule right there for the change of base formula. The log base b of x is equal to the log base a of x divided by the log base a of b, and so on and so forth. So you can switch back and forth. If you need a refresher, there's plenty of resources on the internet that'll help you remember how to do that, or you can come see me in my office hours if you're super confused, okay? Now, it's usually easier for us, because we have 10 fingers and 10 toes, to understand logs based on powers of 10 rather than powers of e. So we use the base 10 log graph paper, even though SemiLog plots are mostly used for e to the x type functions, right? But they're only different by a constant, and so it ends up not mattering too much. So the power for the pendulum, that was a good example of when you'd use log graphs. When would you use SemiLog paper? Okay, so look here, here's our SemiLog paper. On a SemiLog graph paper, you've got squares that are evenly spaced on your horizontal axis, but you've got a logarithmic spacing in between your squares on your vertical axis. See that? Okay, so this is a good example, this graph right here, of a SemiLog plot of a rocket that's accelerating, okay? Let's see. So what you're doing here is you're plotting it out. Your function is y is equal to a times e to the power of mx. So we have a natural base e kind of exponent here. And then if you take the natural log of both sides of that equation, so I'd get natural log of y on one side, and then the natural log of a e to the power of mx on the other side. Now when I take that out, I get natural log of a plus the natural log of e raised to the power of mx. But the natural log of e to the mx is just mx. Okay, so we end up with, when we take the natural log of both sides, ln of y is equal to ln of a plus mx. Right? So this is why SemiLog graph paper is great. You can see that I'm linear in x here. So the regular spacing on my horizontal axis works great. But I have a logarithmic spacing on my y values, and so that's why you use semi-log graph paper, which means logarithmic in one direction and not logarithmic in the other. Okay? So that's what's going on there. Now, you're probably thinking to yourself, why do I care? Okay? I'm just going to do these plots in Origin or something anyway, so why do I need to know that? Well, there's options within Origin for you to make your plot a linear plot, a log plot, or a semi-log plot. Okay? And if you do that, then it can take a function that is nonlinear, like y is equal to a e to the mx, and make it linear. And sometimes that's useful for people to understand what's going on conceptually. So if you have an exponential power, you take the logarithm of both sides, now you have a linear fit, and sometimes you need that slope from the linear fit for various things. Okay? So it helps you conceptualize and understand what's going on in these different types of plots. Okay, so hopefully after this lecture you understand a little bit better about, first of all, what's a linear plot, what's a log-log plot, and what's a semi-log plot, right? So hopefully you understand that a little better, and when you might use each type of plot, and hopefully also you understand a little bit better what we're looking for when you create plots for Physics 2210 and Physics 4210. Okay? If you have any questions or you need any help, feel free to stop by my office hours, and I'll see you in class.